Okay, so it's a very great pleasure to be here. I was a postdoc at the IOA in the early 2000s, and a lot of the work I'm going to present really stems from that era. So I'm here representing the NERSPEC Instrument Science team, the spectrograph on JWST, and also the JADES team, a collaboration between us and the NIRCam imaging instrument. So Steve Finkelstein has just given a brilliant overview of the first couple of years of JWST, but I'm going to ask you to cast your minds back all of 2 years in the era before JWST and where the state of play in the high redshift universe was. So there's a breakthrough about 30 years ago by Chuck Steidel, who understood that imaging in different filters gave a poor man's spectroscopy, and you were able to isolate potentially high redshift galaxies through the effect of this blanketing of the gas between the galaxies, the Lyman alpha forest, eroding the flux, and below the Lyman limit, essentially it was illegal for photons to get through. So galaxies at high redshift apparently disappeared at short wavelengths. So you could separate them out from low redshift galaxies. And Steidel and his colleagues went rapidly from redshift 1, which was the frontier then in the early 90s, to redshift 3 with thousands of spectroscopically confirmed galaxies. And then, thanks to the sensitivity of HST, the Hubble in the imaging, we were able to, and this is work done, started in Cambridge with my student Elizabeth Stanway, Richard McMahon and Richard Ellis, able to isolate galaxies at redshift 6 through dropping out in everything in the visible, so below about 0.8 microns. And we were counting red dots in Hubble Space Telescope images and trying to convince people that these were really high redshift. And then for a few years, heroic work done in collaboration with Richard, with Keck. Occasionally we would take spectra and see Lyman alpha in emission, but usually we would not. So we had, and other groups as well, had a mixed time trying to get spectroscopically confirmed samples of galaxies at redshift 6 and beyond. So why was this so difficult? So you were restricted from the ground and from Hubble to the rest frame ultraviolet. So the strongest line was supposed to be Lyman alpha, but we know this line is highly resonant. It plays cosmic pinball getting out of a galaxy. It's scattered around. It's easily absorbed by dust. So sometimes you hit the jackpot, more often you didn't. None of the other rest UV lines were particularly bright. Occasionally ALMA in more recent years has seen some of the carbon plus lines at high redshift, but that's the exception. So really, for about 20 years, this field had kind of stalled. We had a lot of samples of photometrically selected sources, but little or no spectroscopic confirmation. So, to summarize, we were counting red dots in Hubble Space Telescope images, and that was 20 years of my life, right? And then the game changer has been the James Webb Space Telescope. So first of all, we're able to, with the NERSPEC spectrograph, go out all the way to 5 microns. And on the y-axis here, this is the redshifts you can access using the familiar rest frame optical lines like H alpha all the way out to redshift 7. If you look at the fainter, potentially UV lines, you can go out to ridiculously high redshifts. Not only that, with NERSPEC, rather than hitting one object at a time, or less sensitively slitless spectroscopy over an area with a high background, you have 250,000 microshutters you can individually open, and you can target your favorite high redshift objects, or alternatively, make your favorite space agency logos. So rather than hitting one galaxy at a time, we're hitting 100 or 200 simultaneously. So it's the multiplex, it's the depth, it's the wavelength coverage to get you to higher redshifts. So as part of JADES, we've had a couple of data releases now. This is a stack. This is wavelength going on the x-axis from 0.8 microns to 5 microns, and stacked up in order of ascending redshift. So up at the top we have around redshift 10, at the bottom more like redshift 1. And you can see your favorite rest optical lines shifting to the right through the redshift effect. This is our first data release from last year that I led. We've had a more recent one led by Francesco Di Eugenio. And just to this blue box here, this is where we're sensitive to with Hubble and the ground. So you can see the parameter space and also the depth, which isn't captured here, is phenomenal. So what have we seen? So we started undertaking the JADE survey just before, just around Christmas or November 2022, and immediately we broke the redshift record. So what you see here, these are genuine spectra. This yellow thing is emission, and you see this, the galaxy goes apparently dark, and it's not like we forgot to trim the overscan regions of the CCD or something. This genuinely, the universe is absorbing all these photons. So this is a Lyman break. This is definitive evidence these are high redshift. If you go a bit deeper, and by a bit deeper, I mean from 19 hours to 65 hours, one of the deepest spectra ever obtained, you can start to see emission lines. So this is a redshift 12.5 galaxy, and we're starting to see carbon lines. So non-Big Bang nuclear synthesis elements about 300 million years after the Big Bang. So this starts to be very constraining indeed. This is Francesco de Eugenio's recent paper. And we've recently broken the redshift record. So you can see on the top panel exactly what I was on about. This blob on the right vanishes at short wavelength. That's because the gas between the galaxies absorbs all that flux, comes out at being redshift 14. In fact, this guy was very lucky to make it on because there's a lower redshift galaxy that shows up at all wavelengths to the left. We thought, well, it's just some dusty extension to that. We'll put it on for a laugh. Pay dividends, you know, you have to be very careful with this. So I've shown you some examples of breaks, but we see line emission, often very, very strong line emission out to enormously high redshifts. So if we do a census of the number of galaxies with very high equivalence, that's a high ratio of the line emission to the continuum, then this grey area, we have a tail out at high redshift. This is the high redshift histogram, this grey and blue area, compared to low redshift. So it seems that higher redshifts, the equivalent widths are higher, so that requires more bursty star formation, potentially low metallicity, certainly a higher ionizing spectrum. So beyond breaking the redshift record, we can actually probe the physics of the interstellar medium, the physics of the star formation in these galaxies. So my postdoc Alex Cameron has done a lot of work looking at the line ratios. A lot of information in this plot, but don't panic. The x-axis, this R23, that basically is a proxy for metallicity. And this y-axis, the ratio of oxygen 3 to oxygen 2, that's how hard the ionizing spectrum is. This grey area is the Sloan galaxies, a ratio of about 0.1. Our objects at redshift 6 and beyond are up here, and these sort of green areas and these crosses, these are so-called low redshift analogues, things that impersonate high redshift galaxies but are rare. So they're called things like green peas, blueberries, various other fruit and vegetables. But you can see immediately that the high redshift galaxies are very different from most of the low redshift population. Low metallicity, you'd expect, higher ionizing slope. Ionizing spectrum. So not only that, we're able to probe the status of the intergalactic medium, and this is through the emergence of this resonant Lyman alpha line. So at redshifts beyond 6, received wisdom has the universe is mostly neutral. Lyman alpha should be mopped up, but in fact we've seen instances where we see Lyman alpha emission, probably because the galaxy is carving its own ionized bubble. So Ayush Saxena, my postdoc, has looked at this. We have an example of a very high equivalent width Lyman alpha emitter at redshift 7.3. I mean, classically, this is illegal because the universe is optically thick to that line, but this has carved out its own bubble, and we see the velocity being very similar to the systemic velocity. So it's not a resonant scattering effect. It genuinely is emerging clean, that line. And more recently, we've got another example that Joris Wittstock has published at redshift 8.3. So a very interesting galaxy at redshift 10.6 is GNZ11. So this has been selected many years ago by Pascal Huche. On the bottom, this is the best effort HST spectrum. So if you squint, maybe there's a spectral break. Now, Pascal heroically claimed this was redshift 10. A few people believed him. But he was right. So we took a spectrum with NIRSpec and just look at the difference of quality. This is the extent of HST, spectral coverage. This is what we have with NIRSpec. Lots of emission lines, including very unusual emission lines of nitrogen. We confirmed the redshift. It was slightly higher redshift, slightly lower redshift than had been previously claimed. But not only that, we found Lyman alpha in emission. This is when the universe is supposed to be optically thick to this line. So that was very interesting. We have another example that will be published very soon out to redshift 13. So Lyman alpha at the high redshift is probing the local state of the IGM close into these galaxies. What's interesting about GNZ11 is, at face value, the oxygen metallicity seems very low. It's less than a tenth solar, you know, what you would expect at high redshift. But it has those highly unusual emission lines of nitrogen I pointed out, nitrogen 3, nitrogen 4. These are rarely seen at low redshift. They're seen very occasionally in some low redshift surveys like Classy, targeting extreme star-forming galaxies at low redshift. Have been seen in some AGN, but rarely. There's been a few more examples since we published of this, about half a dozen at redshifts beyond 6. This galaxy, 300 million years after a Big Bang, has a supersolar nitrogen over oxygen. This is a real pain to explain, or a challenge to explain, because nitrogen takes a while to be synthesized. Why is it there? So this has sparked a whole subfield of literature, including a paper led by Alex Cameron, my postdoc, trying to explain this. You know, it might be runaway stellar collisions, Wolf-Rayet stars, it could be tidal disruption events. Certainly this galaxy seems quite unusual. The emission line ratios indicate quite high densities, perhaps consistent with a broad line of an AGN. So I just have a few seconds, so I'm just going to wrap up. Bottom line, JWST really is working. NIRSpec, most complicated instrument that we know about ever to fly, 250,000 moving parts, the micro shutters, it's working, it's delivering fabulous spectra. We're able to probe the interstellar medium, the star formation in these distant galaxies. The ISM was hotter, high ionization parameter, something I didn't mention, harder emission lines, so it blurs the distinction between AGN and the star formers on the traditional BPT diagrams. We've got spectroscopic confirmation all the way out to redshift 14 now. We've got highly unusual emission line ratios. Now, growing up, being a high redshift observer, I used to believe metallicity just had one letter Z. Now we can measure carbon, nitrogen, oxygen independently, even iron. So we're actually turning this into a real science for the first time at high redshift. We've seen Lyman alpha in emission. That's providing constraints about the neutral fraction, and Gareth Jones, my other postdoc, is working on that. And to build on what Steve Finkelstein was saying, we're able to find and confirm luminous ultraviolet galaxies at redshifts beyond 10, which, you know, might break cosmology or might not. There are various mechanisms that you can boost the UV luminosity with even low stellar masses. So it's been a fabulous roller coaster ride for the next couple of years. The data is out there on the archive. We're doing releases of the JADES and other data, and we are desperately looking for things like population 3 stars. Nothing definitive yet, but watch this space. Thanks very much for listening.